Hey folks, so last time we talked about how we can figure out what the phase of water is, whether it's going to be a solid, a liquid, or gas. And the two things we needed to know for that were the pressure, atmospheric pressure, and the temperature of the planet. Today we're going to focus on that second piece. How do we figure out the temperature of the planet? Well, ultimately, all of the energy that's reaching the planet is coming from the star. Now, it may be converted into other ways or whatever, but the star is going to be the major source of energy from that. So if we figure out how much the planet is being heated by the star, that will give us the effective temperature of the planet. Now, the effective temperature of the planet is the minimum temperature of the planet. So the actual temperature may actually be slightly higher for reasons that we're going to get into probably next week. But you will never have anything that will lower the temperature below that. So when you're working on your project, you may find that, okay, I've got a temperature here and it's a little bit too high. I wonder if there's something going on that might lower the temperature. Not going to happen. If it's a little bit too low, well, then we're going to see that there's something we can actually do. But before we can get into those discussions, we have to figure out how to find that effective temperature. And this is going to be another one of those four-step processes that we're going to use. And again, I strongly recommend that you think about getting that spreadsheet set up so that it'll do all the work for you. Okay, let's get started. Okay, so when we're trying to figure out how to come up with an expression for the effective temperature, what goes into determining how hot the planet's going to be? One of the key things here is we assume that the amount of energy that goes into the planet is equal to the amount of energy that's being radiated out from the planet. That amount being radiated out is going to be the effective temperature of the planet. Now, a lot of people in the lab this week get really confused with this. They go, there's a part with the lab where it's going to say, okay, let's suppose that 50% of the energy that comes in gets radiated out. So the other 50% stays on the planet. And what's going to happen is that means the planet's going to get warmer and warmer and warmer because energy keeps coming in, but the same amount isn't going out. Well, then the planet would eventually just melt. All right, well, that doesn't actually happen. Same thing, if the planet reflected back more energy than it's actually receiving, then it's going to get colder and colder and colder, and eventually it's going to become an ice ball. Well, that also doesn't happen. You always have this equilibrium, this balance between the amount of energy coming in and 100% of the energy coming in goes out. From that, we can figure out the predicted planetary temperature because that energy being emitted is going to be the temperature of the planet. So T effective is what we call the predicted planetary temperature. That's what we predict the temperature is going to have strictly based on the amount of energy that it's getting from the sun. So there's three things that it's going to depend on. First of all, the luminosity of the star. How bright is the star? You know, if you've got this big honker O-type star, it's putting out a whole lot of energy. The planet's going to be hotter. And we've been saying that all along, right? You know that. If I've got a really hot star and the planet's very close, the planet's going to be hot, right? So it depends upon the luminosity. The second thing then also comes in there, and that's the distance from the star. Let's say I have an average G-type Earth or Sun-like star. If I'm in too close, it's going to be too hot on the planet, right? If I'm too far away, well, then it's going to be too cold. On the other hand, if I'm just right, then I might be at a temperature where I could have liquid water. So not only does the brightness of the star, how much luminosity it's putting out matter, also how far the planet is from the star is going to matter. And then the third one is something that's going to be new to you. It's not something we've talked about up to this point, and that's albedo. So let's talk about that for just a second. Albedo is how easy it is for the planet to reflect light. So I've got this planet here, and you know how this works. If you've ever been walking barefoot in the summertime, would you rather walk on white sidewalk or black asphalt? Okay, in Phoenix, you'd probably rather not do either one, right? But that black asphalt is going to be extremely hot. Like it's going to cause your feet to blister from that. And the reason for that is that dark material absorbs a whole lot more energy than the white. It's going to reflect it. So we say that the white sidewalk has a high albedo, while the dark asphalt has a low albedo. This is also why you generally want to wear light colored clothing in the summertime because that's going to reflect that light out instead of absorbing. If you're wearing a black shirt like this in the summertime, you're just absorbing that heat and you're actually going to get hotter. So we call a high albedo planet to be highly reflective. Now, albedo goes from 0 to 1. It's never negative. It's always a decimal. It goes from 0 to 1. If it's near 1, something with an albedo of 1 is a mirror. It's a perfectly reflective surface. So, 0.8, 0.9, things like that are going to have a really high albedo. On the other hand, a low albedo, something close to zero, you know, zero point 0.1, zero point 0.2, something like that, is going to absorb more energy. So let's say I've got two planets, and let's say that, you know, it's a set distance away. If that planet is black, if it's got a low albedo, something near zero, it's going to be warmer than a planet at the same distance from the same star that's got a higher albedo, that's reflecting that energy away. And if you think about it, that just makes sense, right? Okay, so what we're going to do now, look in about the middle of your first page. We're going to do some thinking about this, about which one's going to be higher and which one's going to be lower. And so I want you to pause the video after each one of these so that you've got time to think about it. So for which of these is going to make a hotter planet? So when we're talking about the luminosity of the star, stellar luminosity, which is going to make a hotter planet? A high luminosity or a low luminosity? Pause the video and think about it. You probably got that one right away, right? That high luminosity means the star is brighter. It's going to be putting out more energy. So at any given distance, that planet is going to be hotter. All right, now let's do the same thing for orbital distance. This is the distance from the planet to the star. So which is going to be hotter, a large orbital distance or a small orbital distance? Pause the video, think about it. And this one you probably knew as well. We've been talking about this from the beginning and probably knew it pretty instinctively. So the closer that planet is to the star, the hotter it's going to be. So a small orbital distance is going to make for a hotter planet. Now, here's the new one. What about albedo? Which one is going to make a hotter planet? A high albedo or a low albedo? Pause the video and think about it, and then come back. All right, what did you choose? So that high albedo is going to be reflecting the energy away. The low albedo is going to be absorbing that energy. And so that low albedo planet, that darker colored planet, is actually going to be warmer. And just as a side note, this is one of the methods that's been proposed for terraforming Mars. Mars is just outside of our habitable zone. It's just a little bit too cold. So one idea is to sprinkle black dust, carbon dust or something like that, on the poles. And then that will absorb more heat, which will cause that gas that's trapped in the poles, that's frozen, to actually warm up and then give Mars an atmosphere again. So the darker the planet, the hotter it's going to be. Now, albedo is always measured just from the telescope. So this is another thing that's just going to be given to you. You're never going to have to calculate the albedo. It'll always be a number that's given to you. So if we're going to figure out what the effective temperature is, I need to know how much energy is reaching the planet. Well, the amount of energy that's reaching the planet is the flux. Now, we've talked about stellar flux before, way back at the very beginning of the class. That's how much light from the star is reaching us here on Earth. Here, we're talking about how much light from the star is reaching the planet. Okay, so this is the flux at the planet, not all the way out here at the Earth. Now, all the way out here at Earth, that's a tiny, tiny amount. But when you're talking about how much energy the planet receives from its own star, that's going to be a lot higher. And generally, you're looking at hundreds to thousands, somewhere in the tens, hundreds, or thousands. If you're getting something outside of that range, then there's probably something wrong. You need to look at it. So the amount of energy that comes from the star doesn't care about the albedo, right? The star is just sitting there fat, dumb, and happy producing its energy. And the two things that are going to determine how much energy is coming from the star are the brightness of the star, that's its luminosity. If you think about it, we said that as the luminosity goes up, the temperature is going to go up because the amount of flux is going up. So those should both be in the top. On the other hand, if you go back to our table here, we said that a small orbital distance means it's a hotter planet. So those are inversely proportional. So the farther away I am, the less energy I'm going to get. So as this number gets big, this number will get small. And as we've talked about before, it falls off as 1 over r squared from here. The 4 pi comes in because it's actually the light is moving out in a circle, or in a sphere. That's all we really need to worry about. So the luminosity here, though, has to be measured in watts. We can't do it in solar looms. So what does that mean? We're going to do a conversion. So we're going to convert from solar looms into watts. You guys know how to do that. If you're not sure, go back to the conversion tool and review that. The other thing is the orbital distance. We normally have that in AU. Students will mess up and they'll put this in AU. It has to be in meters. So you're going to have to convert that orbital distance from AU to meters. If you don't, you're going to get a really ridiculous answer from that. So again, this number should be, somewhere tens, hundreds, thousands, somewhere in there. Shouldn't be getting tiny, tiny numbers. All right, once you've calculated the flux, then we put it in the effective temperature formula here. So this is the effective temperature tool. This is what you actually want. And yeah, we could have taken this and substituted it in here, but then this formula starts to look really complex and weird. So here's our albedo. Notice that it's 1 minus the albedo. The reason for that is albedo is defined based on how reflective it is. But we want to know how much energy is coming in. So we want the opposite. So that's why the 1 minus albedo comes in. Basically just, except that if I have 0.9, so that should be a very cool planet, right? 1 minus 0.9 is 0.1. So that's going to make this number really small. It's going to be a cool planet. On the other hand, if the albedo is very low, say 0.1, then I should have a hot planet because it's dark, right? So 1 minus 0.1 is 0.9. And so that flux is going to be the total temperature from the flux is going to be quite a bit higher. This number here, this sigma, this is a constant. You don't have to memorize this. It's given to you on your equation sheet. It's one of the easier ones to remember. It's 5.67 E minus 8, so 5678. But you can always look that up. You never have to memorize that. The other thing you want to be careful about is you're raising the whole thing to the 0.5. If you really must put this in all at once, and of course for a spreadsheet you'll have to, you're going to want to make sure that you have an extra set of parentheses. So you want to set a parenthesis around the flux, and then a second set around the albedo, then divide, then a full set of parentheses here, and then finally raise to the 0.25. If you need help with that, come by live help, and I can help you get that set up. All right, so let's go through the steps here. Look on the back on page 2, and let's go through the steps and figure out how we can figure out the effective temperature of this planet. So let's suppose that I have a star that's 1.5 solar looms. So it's 1.5 times as bright as the sun. So it's brighter than the sun, but the planet is twice as far away as Earth. So it's 2 AU away. So maybe good, right? The star's brighter, but the planet's farther away. The albedo is 0.5. That means it reflects out half the energy that it receives. So we've got 4 steps that we're going to do here. And I'm just going to outline them here first, and then we're going to go through them one by one. So we're going to convert the luminosity from solar looms to watts. Then we're going to convert our orbital radius from AU to meters. Don't forget to do that. That is the place that most students mess up. Do your conversions before you try putting it in the formula, or you will get the wrong answer, guaranteed. After you've done that, we're going to get those 2 numbers. You put them into the flux tool, and you're able to calculate the flux. Once you've got the flux, you put that in with the albedo, and you've got the effective temperature. All right, here's our constants. These are our conversion factors. These are not equations. They are conversions. They're things that are the same. So 1 solar loom is the same as 3.827 E26 watts. 1 AU is 1.496 E11 meters. All right, so first step, let's do our conversions. So here I've got it set up for you, but I want you to go through the math and actually work it out, and let's see what you get. Pause the video, do that now. All right, so you've got 1.5 solar looms. I want the solar looms to cancel, so I'm going to put it in the bottom. So remember, start with your units here. So I'll put my solar loom in the bottom, and I'll put my watts in the top. Then the numbers are glued to the units. So the 1 is glued to the solar loom. The 3.827 E26 is glued to the watts. The solar looms cancel. That's good. Leaves me with watts. 1.5 times 3.827 E26 divide by 1 then gives me 5.74 E26 watts. And you've done something similar to this before. So this is a really big number. This is a lot of power. Well, it's a star. I would hope so. So this is the number that's going to go into my flux calculation, not this. You should always be working with big numbers when you're putting things into calculating the flux and the effective temperature. All right, so we're going to store that one up here. Now, step 2, I want you to do exactly the same thing. I want you to convert that 2 AU into meters. Use this conversion that's down here at the bottom. Pause the video and do that now. All right, you got it? So we set up our conversion the same way. What I want times the fraction bar. I want my AUs to cancel, so I'm going to put it in the bottom. I'll put the meters in the top. The 1 is glued to the AU. The 1.496 E11 is glued to the meters. AUs cancel. That's what I want. 2 times 1.496 E11 divided by 1, then you should get 2.99 E to the 11. So we're going to store this up here. Your next step is to calculate the flux. So we've got our two values here. You just need to plug those into the flux equation. So here's the flux equation right here. You're going to put this number in for L and this number in for the orbital distance. Pause the video, work it out. Okay, back? All right, so plugging in those numbers then, the 5.74 E26 goes here, the 2.99 E11 goes here. Multiply all that out, and you get that the flux is about 510, 511, depending upon where you're rounding off. I think it actually comes out closer to 511. All right? So if you're getting 510, 511, you're going to be fine. Yeah, I've got 511 on that slide. All right, so now I want to calculate the effective temperature. So now I'm going to use this formula, and you've got the flux, you've got the albedo. This number is a constant. Remember, it's 5.67 E negative 8. So you can pull that off of your equation sheet if you don't remember that. So plug in your numbers, and let's see what you get. All right, so we're going to take our flux, we're going to put it here, we're going to take our albedo, we're going to put it here, we're going to change this to 5.67 E negative 8, which is this value right here. And then all you got to do is plug it in. Now, make sure, what I like to do is I'll do this part with the parenthesis, I'll hit equals. I'll divide by this with the parenthesis, and then I'll hit equals. And then I'll raise the entire thing to the 0.25. All right, now I'm going to give you a little quick tip for those who are comfortable with the math. Raising to the 0.25 power, it's the same thing as hitting the square root button twice. If you don't like that, close your ears. You don't need to hear that, and just raise it to the 0.25. But if you're comfortable with it, you can speed things up a little bit by just hitting the square root button twice. All right, so when we figure this out, then I'm getting 183 degrees Kelvin. All right, so is it suitable for water? Well, just knowing the temperature isn't enough. Remember, that just tells me where to start here, but I need to know how far to go up, so I also need the pressure. So let's assume that this planet has the same atmospheric pressure as Earth. So it's 1 atmosphere of pressure, and it's 183 degrees Kelvin. That's going to be right here. So it's going to come up to here, looking at your water phase diagram, and that means the state of the water is going to be solid. So this is not a habitable world. All right. Okay, so the practice problems for this week, we're going to give you 2 actual alien planets, one of which is Alpha Centauri b. That's actually the next star system over to us. Yeah, we've actually found a planet right next to our own solar system, so that's kind of cool. And then we're going to have you do the calculations for Venus, Earth, and Mars. All right. The last question on that sheet I want you to think about. So based on the water phase diagram, it says, does Earth have the right temperature for liquid water? Based on the water phase diagram, not based on your own experience necessarily, based on what the water phase diagram comes into play. And then there's something that the effective temperature is not including. See if you can figure that out. And if you're stuck, come by Live Help and we'll talk about it. Okay, so now we know how to find the effective temperature of the planet. And what you're seeing is that this is only the temperature of the planet due to the energy coming in from the star. There are some other things that are going on that we're going to talk about next week from that. But for right now, that's where we can start. And the thing I want you to remember is this is the minimum temperature of the planet. The planet will not be any colder than the amount of energy that it's getting from the star. So once we calculate this, we've got a minimum. It's not to say it couldn't go up. And like I said, next week we'll talk about what can make it go up a little bit from there. All right, we'll see you next week.